Not so bad. About that? Yeah? So, am I waiting for anything to start, or should I just begin? Just begin? Okay. Morning, afternoon, everybody. My name is Seth. I'm going to be talking on learning OpenPGP by example, or stupid crypto tricks with GPG. There's a reason for that subtitle, so just bear with me and you'll see what I'm talking about. So I'll just give a quick introduction first. What am I going to be doing with the next hour of your time? The primary goal of this talk is to help teach people about how you can use crypto in a very easy way through what's already out there. Very nice standard OpenPGP does basically everything you need, and there are interfaces to it, that implementations that let you do basically whatever you want. To do this, I'm going to be showing off some tricks and possibly some code that I'm probably going to regret releasing later on because, you know, stupid crypto tricks with GPG. As a little background, this started off as a very serious lecture about the standard and what you can do and what you can't do and how one would go about improving it. And as I worked on the examples, the seriousness just deteriorated because I was working on fun things and I'd work on something and I'd go, hey, what if I do this? Oops, I probably shouldn't be doing that, but what the hell, I'll do it anyways. So the serious level has sort of deteriorated over time. So expect a half-joking presentation, but everything you'll see here is accurate and correct to the best of my ability. If anybody has any questions at any point during, or if you don't understand something, if I'm talking too fast, just sort of raise your hand and wave at me and tell me to slow down or to repeat something. That's fine with me. So I guess I will begin with a disclaimer. If you have a strong background in crypto or a very good understanding of the OpenPGP RFC, you're probably not going to be as entertained by this as I'd like you to be. But if you're not very familiar with the internals, if you're just getting to know what sort of things you can do, then hopefully you'll be entertained. We'll cover three main areas. We'll look at higher level stuff, keys, signatures, and using a OpenPGP implementation written in Perl, crypt OpenPGP module. Then we'll move to some lower level stuff. We'll be looking at some of the source code to GPG. It won't be terribly in-depth because there's not much you can do in front of however many hundred people are here, but it'll at least give the general ideas and where you would want to go if you want to do some extension work to it. And at the end is going to be the fun part, some attacks and obnoxious tricks. This is the part that I'm probably going to regret releasing later, but I guess we'll just see how it goes. And this should be enough to give people a general idea how to continue with this sort of work on their own, sort of what they can do, what they can't do, and how to piss off a whole lot of people who currently use OpenPGP, PGP, GPG, Web of Trust. So we'll start with the higher level stuff. Anything that you can do with PGP, GPG, whatever, you can do very, very easily in Perl. Somebody was nice enough, Benjamin Trott was nice enough to go out and to do a full implementation of everything that OpenPGP can do just about in Perl. So if you want to do an encryption program, you can do it in maybe 30 lines of Perl. If you want to do digital signatures, you can do it in about 20 lines of Perl. If you want to do key signing, key verification, anything like that, absolutely simple. This is actually how I taught myself Perl. I didn't know any Perl, but I found this module and I said, hey, this looks like it could make things easy. And it did. Not only did I get my work done, I also learned Perl in the process. So it was pretty nice. It's compatible with the 3 major flavors of PGP out there. There's GPG, which mostly tries to stay as RFC compliant as possible. And then there's PGP2 and PGP5. PGP2 is deprecated, probably shouldn't be using it anymore, but a lot of people hold on to it and have the attitude that they'll stop using it when you pry it from their cold, dead hands. So maybe one day they'll upgrade, probably not. The other nice thing about all this is the code is open and reusable. Some of the proof of concept code that I wrote relied on some implementations that were already out there. Because the code was there, I could just pull it and reuse it, and minimal amount of work in order to get a full application written. And that application was a subliminal key reconstructor. This is where all of this started. It all started with a joke at Black Hat Europe, actually. Somebody was talking about subliminal channels, and I mentioned the one in the digital signature algorithm, DSA, which is common on all new PGP keys. There's a subliminal channel in it that if you have a backdoored encryption application, it can be configured to leak your private key every time you make a digital signature, and it's completely undetectable. There's no way of finding that it did this, even if you have the signature that you've made. So I wrote a little program that consisted of a patch to GPG that would backdoor it, and a Perl program which would take a signature and it would pull the private key out of the signature. So it would read in a signature, read in a public key, do some intermediate processing, and write an ASCII armored secret key block out, which was the signing key of the person who made the signature. So this is all a feature of DSA. This was discovered shortly before the United States government chose to adopt it as an official standard, so can't exactly call it a bug. Whether you trust it or not, it's entirely up to you. It's probably no worse than RSA, so it's nothing to be afraid of, really. But it's out there, it exists, and I wrote a program that does all of this in Perl in a fairly minimal amount of time, and in the process learned a whole lot about how the internals of keys work, signatures work, and all the other parts to it. So looking at signatures and keys, there are 2 main versions being used right now for these signatures and keys, version 3 and version 4. Version 3 keys and signatures are everything made by the PGP2 programs. They're RSA only, and you shouldn't be using them for a number of reasons. There are a few main potential security problems with them, including use of MD5 as a hash, which isn't as big of a deal now that SHA-1 is close to being broken, maybe. There's also issues with being able to easily clone a key ID with it. If the key IDs have a very specific form, and you can clone key IDs and cause all sorts of confusion that way. So RSA v3 keys, probably shouldn't be using them. v4 keys, they're what everything else uses, PGP5, OpenPGP. They can be DSA, RSA, whatever. I'll talk more about them in a bit. And the keys and signatures and all of the OpenPGP stuff, they're handled in packets. So your key data is in a packet. A signature is in a packet. The signature packet has sub-packets. There are encrypted packets, plain text packets, user ID packets, photo ID packets. Everything that you want has a very specific form, and it's fully outlined in the RFC. So I'm not going to bother you with all of the details, because I could give you tables of algorithm numbers and identifying numbers, and none of you would really give a shit. So I'm just going to skip that and give you a higher level idea of what's going on. And if you would like to know more, just look it up in the RFC. It's very nicely detailed there. So everything is done in packets, including sub-packets. All of your preferences and timestamps and policy statements and everything, they're all in packets, and the packets can be manipulated, they can be added, they can be deleted. You can basically do whatever you want with them. And these Perl implementations make that a lot easier. So v3 keys. Here's the structure of a version 3 key packet. The first octet is the version number, which is 3, obviously. Then you have a 4-octet timestamp. The timestamp is the creation date of the key. And then there's an expiration date, which is in 2 octets, which is the creation date plus however many days. So if the expiration date is 5, then your key is valid from 5 days after the creation timestamp. There's 1 octet for a public key algorithm, which is always RSA, because RSA is the only algorithm that v3 keys use. And then you have a few octets after that, which contain the public key values N and E. So your N is the large public modulus, and E is the encryption key. So all you do is you take your message, you raise it to E mod N, and you have your encrypted message. The key ID in this case are the low 64 bits of your public modulus. Now, it's not terribly difficult to recreate the same public modulus, especially if you made a key in the first place. So if you're fairly tricky, you can make keys with the same key ID, even though they have completely different key data. And the fingerprint will still differ, because the fingerprint is just a hash of the key material. But if somebody doesn't check fingerprints religiously, then they might see a key with the right user ID and the right key ID and go, okay, well, I mean, if the key ID is correct, then it's got to be the right key, right? And no, it's not. There are ways around that. The fingerprint, the other problem is, this is an almost fixed length packet. It can vary a little bit, but in practice, it's usually about the same. And the hash of the key material to make the fingerprint doesn't rely on length, which means the key space for doing a collision search is smaller, because you're working over an arbitrary length. You can do it over a large length, and it doesn't matter because the length isn't taken into account in your fingerprint. So this is one of the security reasons for possibly not wanting to use v3 keys. v4 keys. This is what most people are probably using these days. It's fairly similar. There's one main difference, or two. The first octet is the version number. Now it's 4, v4 key. 4-octet timestamp, same thing, creation date. 1 octet for the public key algorithm, but now that public key algorithm is not limited to being RSA. You can have it RSA, you can have it DSA, you can have it El-Gamal. Supposedly you can have it other things such as ECC, ECDSA, even though they haven't officially been defined yet. And then the last octets make up a more variable length field, which contain, again, the public key values, but now instead of just having N and E for RSA, you can have P, Q, G, and Y, which would be for DSA, or PG and Y, which would be for El-Gamal. So different algorithms mean different parameters, and there is a very set way of representing the parameters for each algorithm. And this is the reason why there hasn't been additional algorithms added to the OpenPGP standard in the 10 years it's been around. I'll get to more about this later. But the key ID, low 64 bits of the fingerprint, simple enough. The fingerprint is a SHA-1 hash of 99 hex, the length of the key packet, and then the key. So it's dependent on length, so you don't have that same length-based key space search. And it's fairly difficult to copy a fingerprint, supposedly. I mean, there's all this talk about SHA-1 being broken or almost broken, so who knows? But as far as I know, as far as most people know, I'm guessing, it's very difficult to copy a fingerprint. There's a program out there called PGP dump. It visualizes these packets in any sort of OpenPGP encoded material that you have. So you can have a public key block, a private key block, an encrypted message, a signature, and you can run it through this program and it will show you the structure of the data and the values inside of it. So in this case, I don't know if you guys can see it. Is this too small? Can people see it? Okay, so what I did was I ran the beginning of my public key through the program, and you can see that at the top you have a note saying that it's a public key packet. In this case it's tag 6, and it's 418 bytes long. It's a v4 key, so you've got your version identifier there. Then you've got the timestamp. So I don't know if I can go back here. You've got your timestamp, which is the second field, which is the creation time. Then the third field is the algorithm identifier. In this case, it's DSA, which is 17 hex. And then you have your 4 DSA values. You've got P, Q, G, Y, and it gives you the length of each. And it doesn't actually display them here because, you know, who wants to see that? But you can go in and you can pull out the values if you want. And then the next thing you see is a user ID packet. In this case, it's tag 13. These tags identify what the types of packets are and thus what kind of data comes in them. So as I said before, everything is done in packets, and a user ID packet contains your name and your email and any comments that you have. It's what you get to type in when you're generating a key. It's just text. You can basically put more or less whatever you want in there. In this case, it's my name and my email address. So this is the beginning of my public key. Some observations about keys. The key ID of a v3 key, it's the low bits of a public modulus. As I said before, it's relatively easy to make keys with duplicate key IDs. This can be a problem. I mean, if you're doing everything like you should, then it really shouldn't be a problem because you'd verify the fingerprint as well. But a lot of people I've noticed in practice just don't do that. The length of the v3 key isn't taken into account for the hash, so you can try to do a key space collision with an arbitrary length string instead of a fixed length string. And the v4 keys are a lot more flexible. And this carries over to v4 signatures as well. The signatures, I'm not going to get into all the details here, but rather than have just the fixed block for the signature values that you would get with an RSA key, you have different possible types of subpackets. Because in a v4 key, you can have any number of different signing algorithms. So one packet, one format isn't enough to do. So they're a lot more flexible, and you can put RSA data from a v3 key into a v4 key, but it will completely change your fingerprint and key ID and all of that. So you might not want to do that. So more about the key IDs and fingerprints. If you change the timestamp, it'll change the fingerprint and possibly the key ID as well. The algorithm parameters for v4 keys, in this case P and G, they're public parameters for the crypto system, so they're used to create the entire crypto system, but they're not actual key material. They can be reused, but again, it will also change the key ID and fingerprint because you're not going to reuse the actual key values, in this case, say Y, and changing that will change the key ID and fingerprint because it will change the hash. This might seem trivial. So, you know, okay, you can change the timestamp, you can reuse parameters, it'll change things. Why is this important? Well, I wanted a vanity key. What's a vanity key? Your key ID, 8 hex digits. So with a little finagling, few hacks here and there, You can accelerate key generation to only look for keys that you want, and you can keep doing it until you find one with the key ID that you want. In a v4 key, again, it's the low order bits of the hash. So all you're doing is you're looking for a partial hash collision. This sounds fairly difficult, but if you're using something like hashcache, it's the exact same thing. So in this case, it's like generating a 32-bit hashcache token. It's a good amount of processing power, but it's easily distributed. And if you use these tricks like fuzzing the timestamp a little, changing it up and down, you can generate keys faster than would be possible by just batch mode generating them over and over again. If you keep the parameters the same, you don't need to regenerate them each time, and that takes a long time, relatively speaking. So if you do the key generation, you'll see the dots go by in GPG, and it usually does it in 2 chunks, once for the parameters, once for the keys. If you keep the parameters the same, you only need to do one of those, and it's usually the faster one because you only have one modulo exponentiation involved. So it's a lot faster. So the point of all this, trying to make a vanity key so your key can be, dead beef or whatever you want it to be. Don't you want to show off your key and be like, oh yeah, well, my key is dead beef. So it's stupid, but it's fun. And it's all about, street cred, showing off and going, look at me, my key's cooler than your key. It's really all it comes down to. So that leads into the part on actually getting into the program and looking at the source code. So how hard would it be to implement this vanity key generator as a new key type? So in GPG, when it asks you what key you want, couldn't you just say, well, I want a vanity key, I want it to be this key ID, and have the key generation take longer? Well, if you look into the source code, you find in the public key definitions file, you have a table. And the table effectively just holds parameters and function pointers to the important operations of each algorithm. So you've got a pointer to a generate key function, a pointer to a function which checks the validity of the secret key. Encrypt, decrypt, sign, verify, and get the bits of the key. So standard functions, relatively easy to implement. And if you want to put in a new algorithm, you just have to make these functions and stick it into the table. How does key generation go, though? There's a function, in the keygen file, there's a function called doGenerateKeyPair. Okay, so you want to generate a key pair, that gets called, and it goes down to a function called doCreate. Okay, we're going to create a key, which goes down one level and calls a function of just generating specifically a DSA, RSA, algomal, whatever key. And then that function goes down to the cipher table level. So each gen function will call by name the functions in the cipher table, which works, but it means that if you want to add another algorithm, what you have to do is you have to add it to the cipher table. Then you have to make another one of these functions, so you'd have to make a gen vanity DSA or whatever you want to call it. Then you would have to add that to the doCreate function, and you would have to add a way of calling it with that specific key type in the doGenerateKeyPair function. So it cascades all the way back up. The problem with this is these functions are already defined, and they only allow for certain parameter passing. So if you want to generate a vanity key pair, you would need to say, well, this is the key ID that I want, and you would have to pass that down. And if you wanted to reuse the parameters, you would have to tell it somehow, reuse these parameters. And in this case, there's no way of doing that, because when you go down the function stack, you call them and then they return. And in this case, there's no way of saying, okay, we'll go down to gen DSA and reuse the same functions and stay in there. There's no way of currently doing that. So adding vanity key generation to GPG right now, it's pretty difficult. Something I'm working on, but it's not going to be nearly as easy as it could be. What about adding other algorithms to GPG? Well, there are other algorithms defined in the OpenPGP standard. For example, 18 is reserved for elliptic curve crypto. 19 is reserved for elliptic curve DSA. So these numbers are reserved, it's already in spec, why not add it? So all you'd have to do is add the algorithm to the cipher table. So you would add another entry in the table saying, okay, we're going to define an algorithm, type 18, here are its parameters, here are its function pointers, you can call it. Then you have to add the standard functions in addition to the function pointers, well, up in the actual GPG code. So how there was the generate DSA, generate RSA, you would have to add one of those functions. That's not so difficult. You would have to change the next one up to allow for calling a generate function of that key type. Again, not so difficult. The reason this isn't difficult, but the vanity key generation was, is because you're not passing any parameters here. You're just saying, okay, make me a key of this type, and you're not trying to reuse things, you're not trying to tell it to look for a certain key ID, you're just saying, go ahead and do it and give me what comes back. So it should be really simple, right? Well, the spec is about 10 years old, and nobody's done it yet. It seems kind of weird, right? One of the big problems with why nobody's done it is because, remember in the description of key data, how in your public key values were N and E, or P, Q, G, and Y, or PG and Y? There is no standard way of specifying the parameters for elliptic curve crypto. So in this case, it would be more or less the exact same parameters as an Elgamal system, except instead of having specific values for your parameters or keys, you would have points on an elliptic curve. So you would also need representation of an elliptic curve. You would need a standardized form for doing curves. You would have to decide if you're going to do a curve over a prime field or a binary field, whatever. There are no actual standards for defining these parameters yet. And, well, you know, it's been 10 years. I think it's about time that we had elliptic curve crypto and GPG. So I'm working on it. And if I finish before any of you do, I challenge you to try to beat me. If you finish first, we'll use your standard. If I finish first, we'll use mine. Or at least you'll use it if you want to use elliptic curve crypto and GPG. It's something I'm working on. Maybe one day it'll actually be accepted into spec. And even if it's not, you know, what the hell ever. I want to use elliptic curve crypto. So we'll see what happens. So that was pretty interesting, right? Yeah? Yes? No? Yeah? So, no, not yet. There's more. There's more. I just wanted to see if you guys are still with me. Hoping, you know, your eyes aren't glazing over yet. This is where the seriousness of the talk starts sliding. You know, vanity key generation might be kind of silly, but, you know, hey, at least you can show off your vanity key. But now we're going to get into things that I might regret talking about later. So let's start here. Okay, who here uses GPG or PGP or whatever? Can I see a show of hands? Okay, how many people here have generated a key, submitted it to a key server, and then lost the key? Either by forgetting a passphrase or losing the secret key block. Okay, good amount of people. You know what? I've done it too, so I can't really make fun of you. What happens to the key on the key server? Okay, so you're supposed to generate a revocation certificate when you make the key, and you're supposed to put it in a safe place. And if you've got a safe place, you might as well put a copy of the key there too, so you won't lose it. But, you know, somehow a lot of people forget to have these revoking certificates. I've got one on a CD in a fireproof safe. How many other people have something like that set up? Anybody? One. Okay, so we've got a few people here and there. Most people don't. And this is a problem because if you lose your key, then your public key stays on the key servers, and it's not marked as revoked. So anybody who's looking for your key will find it. And if you just generate a new key, then, well, how do they know which one is the right one? You know, you can say, okay, well, I lost a key, so use the one with the more recent timestamp. But the key stays around in the key servers and never comes out, ever. So, remember how I said vanity key generation is basically generating a whole lot of keys until you find one with a partial hash collision of a fingerprint? So you got to generate a whole lot of keys, and you got to generate them really, really fast. So, you know, how fast is key generation if you reuse parameters? What if you don't even care about whether the key is valid and you just stuff bad data in there? What if you otherwise fuzz values in order to speed key generation? Okay, can people see where this is going? Get an idea of what I'm doing here? How big is one key? Well, it's a little under 2K. That's with no signatures on it. I run a key server on the SKS network. The key dump of every single key in the network, last I checked, was about 80 gigs. 2? It was only 2? 2 in the database because... oh, okay, the database is 80 gigs. Okay, the dump... No, my database is a lot bigger. Maybe I've got something screwed up on my database then. Okay, so it's not 80 gigs. The dump is a lot smaller, but the database is a lot bigger. I guess my database sucks, and it's doing it a lot worse. I think I should check into that, because if you're getting it in 6 gigs, then I've got a problem. So, okay, ignore that. The key dump is a lot smaller than that, but the point of this is one key, just under 2K. Now, how many keys do you have to make a second in order to reasonably do a 32-bit partial hash collision? The answer is quite a lot. So, what happens if a key goes into the key server network and you want to get rid of it? You can't. I'll just leave it at that. But it gets worse. There are ways to sort of prevent attacks like that. And I mean, people have known about this for ages. This is not new at all. But nobody's done it yet. Nobody's actually been concerned about it happening yet. And if worse comes to worse, if you see a huge flood of keys coming in from one source, you can back up your database, hopefully, and hopefully it won't have propagated. It'll be a huge pain in the ass, but you'll be able to do it. It can get worse, though. So what happens if you generate a whole bunch of keys, don't submit them just yet, use the keys to cross-sign each other, and put valid email addresses and user IDs, real-looking names, and then you distribute the way you add them to the key server network? Is there any way to tell these keys from real keys? The answer is maybe, but it's not going to be easy. So you can just dump all these keys into the key server network, and what happens when instead of having a 4 gig database, you have a 500 gig database? How many key servers will be able to handle that? Mine won't. That'll destroy mine. So everybody has known about this attack for ages. Nobody's done it. Nobody seems to be terribly concerned. Just thought I would point this out. The other neat thing you can do with cross-signing keys is, well, let's try to be even more annoying. Let's pick a key that you don't like, download it from a key server, look at all the keys that have signed it, download those keys, look at all the keys that have signed those, download those keys, keep going out to a certain level of a chunk of the web of trust that you want. Now, generate that many keys. Not so difficult, right? Copy the user IDs from those keys. Stick them into the keys you've just generated. Now you've got a whole bunch of keys that roughly correspond to these real keys. Cross-sign them in exactly the same way that the real keys are cross-signed. Right? What happens next? Well, you upload them back to the key servers, and all of a sudden, if you do a search for somebody's name, you see 2 keys. Now, this shouldn't be a problem, right? Well, how many people check fingerprints? Who here checks fingerprints when they sign keys? Okay, I thought I saw more people than that raise their hands for how many people use GPG. And you know what? If you didn't check fingerprints, you'd probably not raise your hand anyways, because you don't want to be like, I screw up. So a lot of people don't check fingerprints. I know this because I've had friends of mine sign my keys without having my fingerprints, without even checking to make sure the key that they've had is the correct one. So what happens if you've got a fake chunk of the web of trust uploaded to one of these key servers and somebody signs the wrong key? Well, then not only do they sign your key and encrypt to your key when they think they're sending it to somebody else, but it cascades based on the trust from your fake key, which is based on their real key. So they now send their encrypted or signed messages to you when they think they're sending it to a whole bunch of people. Again, it's a very trivial problem, but it's one that people don't really seem to think about. And it doesn't really seem to have been brought into play yet. Signatures. Well, you can do this with signatures too. Signatures don't leave the key server network. Say you want to screw with somebody's key. Generate a whole lot of keys, have each key sign the person's key, and upload their key back to the key server. So you can have somebody's key with thousands or millions of signatures on it that correspond to key IDs that are not in the key server network. So if you try to see the signatures on somebody's key, you'll get this huge list of signatures, and the real data is in there, and how many people are going to want to page through a few million signatures to find the real ones? I wouldn't. I'd get kind of pissed off. The other problem with this is that you can choose the user IDs on those keys if you upload them back to the key server network. So again, I hope you can see this, but what happens if I find some person in American government and generate a key that is called the Al-Qaeda master signing key? Sign their key and upload it back to the key servers. I mean, it doesn't mean anything because nobody's verified the identity on it, but it still looks bad to have something like that attached to your name. There's absolutely nothing that can be done about this. Absolutely nothing. Again, not a new problem, but haven't really seen it in practice. So if you all want to generate Al-Qaeda master signing keys and go have a blast, by all means do so. The best part about it all is you don't need a special Perl program to do this. You just make a key and go. There are a lot of etiquette rules that are supposed to prevent this stuff, but they're etiquette rules, which means they have no basis in reality. I've talked with somebody, I did a key signing party at Hope, and I talked with somebody who was part of that key signing party about these etiquette rules, and he and I had very differing ideas on what proper key signing etiquette is. One thing that he brought up was if you sign somebody's key, you don't send it to a key server. You send it back to them directly. And I mean, yes, I can understand the politeness value in this, whatever, but this is actually good practice because if the email address isn't valid, then they never get the signature, and the signature never propagates. So there is actually security value in this, and you should do it. However, I've seen a whole lot of other things that people get kind of upset about, and it seems kind of weird just how upset they get about it. Like, don't sign somebody else's key unless you've got their permission. Well, if I have somebody's fingerprint and I've verified their identity, I'm going to want to sign it because, isn't that what the whole web of trust is about? Trying to distribute this trust so that you can trust other people through trusting somebody else. Don't sign somebody's key because they don't want you to sign their key. What's the point in having a key if nobody's going to sign it? So it just seems kind of weird. But what's even weirder, has anybody here heard of Big Lumber? I think it's .com or .net or whatever. It's basically a site that coordinates key signing parties, coordinates people who are looking to sign each other's keys. It's there so that you can say, oh, I'm in this part of the country, and you find people around you who are willing to exchange signatures. And it's very useful, it's cool. But one thing that they have is they have a key signature escrow service. And this is an escrow in the sense of they can, backdoor your key so that they can get something if you forget your key or if law enforcement agents need it. This is escrow in the sense of eBay auction escrow. You upload a signature on somebody else's key to their server. The other person uploads their signature on your key to the server. And when both of them are there, it will email you with the signature on your key. So it guarantees that unless both of you sign each other's keys, nobody gets a signature. Am I the only person that sees this as absolutely stupid? Because I just don't understand. And a lot of people get very, very upset about this sort of thing. Like, oh my God, you signed my key and I didn't sign yours, ha ha ha. Look at me, I'm a uber elite hacksaw. Like, what the hell's the point? Like, there's absolutely nothing you can do about it. It's called a public key for a reason. And if you keep worrying about it, then you're only going to keep worrying because there's absolutely nothing you can do about it. So I violate a whole lot of etiquette here, and I'm not sorry. So these aren't new problems, none of these. None of them are new. and they're stupid crypto tricks, but they're stupid crypto tricks that a lot of people just haven't thought about because they just assume everything works okay. And they don't. There are really a lot of things that you can do to cause a whole lot of problems to the entire PGP infrastructure right now, and there's nothing that can be done about it. Are there solutions? Yes, there are. If you validate email addresses before allowing key submissions, you get rid of almost all of these problems. If you require a key to match up to an email address, then you can't do these floods. The downside is then every key has to correspond to an email address, and you might not always want that. PGP, the company, I believe is doing this now. There's something called the PGP Global Network. Has anybody heard of this? Okay, I hadn't until about 2 weeks ago when I got an email from them saying, we have a key with your email address on it, we want you to verify it. And normally I would have just been like, fuck you, spam. But in this case I was like, that's a really good idea. I think I'm going to do some research on it first, but I think I'll go along with it. And it did actually look like it was coming from the PGP Corporation, and it did actually look like it was legit, and it was just my public key, so what the hell do I care anyways? So I said, yes, this is correct, and I uploaded my key to the key server using the special form that they wanted, and I'm now listed in the PGP Global Network or something with my key as being successfully bound to my email address. That helps, but in this case it's retroactive, so there's only so much that can be done, and the current key server networks like PKS, SKS, whatever, they're screwed. So maybe things will start moving in that direction. You can also limit the number of keys submitted. You can either do it based on IP or based on time. None of these methods are foolproof. If you require things like hash cache tokens before you can submit a key, then yeah, it gets better, because then you can't do one of these stupid floods and make every single key server in the network have to have a 500 gig database. The downside is a lot of people don't use hash cache, but then again, if you're savvy enough to know how to use PGP, then you probably know how to use hash cache or could learn it if you were directed to it. The last piece of advice is check the goddamn fingerprint. Come on guys, seriously. Like, don't sign my key if you haven't checked with me and checked the fingerprint. And there are a number of people who haven't, and I see this all the time. All the time. I had a key signing party at Hope, and somebody was there. He was very security conscious, and he was very, very insistent on which keys he would sign and which keys he wouldn't. And he wouldn't sign older RSA keys because they were too old for him. He was concerned that these keys have been around for too long, so obviously this key must be compromised because it's been around for a while. But then halfway through the presentation, he said, well, I just missed out on a whole bunch because I came in late. These 5 names on the list, were the fingerprints correct, everybody? And everybody sort of, gave him a thumbs up, and he sort of nodded and checked them off. I don't know if he actually used that information, but check the goddamn fingerprint, really. Like, it will fix all these problems. So, yeah, the solutions do exist. And, so what have I been ranting and rambling on to you about? Well, all this stuff is pretty simple. If you know how to program, especially if you know how to program in either Perl or C, you can basically extend or re-implement or do whatever you would like with PGP, GPG, whatever. If you are programming a new application, you can integrate it into your application very, very quickly. I'm actually writing right now a key server, not for PGP keys, but for SSH host keys. And the way it works is you can put a signature on a host key, upload it to the key server, and then if you do a search for an SSH host key, well, you can find a key and you can see who has digitally signed it. Then if you trust the person who's digitally signed it, you can trust the host key, right? So if I have a shell server and I've put a digital signature on it, then you can probably trust that that key is correct. Nobody's done this yet, so I figured, what the hell, I'd implement it. In Perl, pretty simple. Everything is already done for you, all the crypto parts. Just call the crypt OpenPGP modules and you're almost done. So this lends itself to fairly rapid application development, and it's not as hard or intimidating as most people would think. Showing you all the little random bits I'm working on here and there that I've started on, all from these subliminal DSA key stealers, vanity keys, whatever. So I've just covered all that. And if you want to be stupid and annoying, all of these attacks are out there. The code's out there for flooding key server networks and copying chunks of the web of trust and making somebody's key huge through putting on fake signatures to it. So what's the point? Well, this is all just a starting point. There's a whole lot more possible. This is just the simple stuff. This is the starting point. Go from it wherever